Alright, we are going to talk about functions of several variables, and hopefully this will not be too difficult a topic, section 14.1. So, our main thing here is we're talking about functions that take in vectors in Rn and spit out scalars in R. It's a machine. That's how I was thinking of functions. It's a machine. You put something in and something else comes out. Now, the domain is pairs of x and y. The range is single numbers, which could be written as z equals f of x. Or we could be in R3, in which case it'd be x, y, and z feed into f, and the thing comes out, you might call w. But what's different than before is that when we were doing lines and space curves, we had a single parameter t determining the shape. So really, there was only one input variable, it was t. If we had been given x, we could have solved for t and then worked out y and z. So the domain is a subset of R squared on which f is defined, and the range is a set of outputs that f achieves on D. Usually we want to think of D as being something connected, like a ball. So, that's what I was just saying about how there's really only one variable for the space curve situation, whereas now we have two input variables that are x and y and sometimes z. Point is, these are independently chosen. When I talk about dimension, what I mean is how many choices are you allowed to make. So a line is a one-dimensional object because once you choose what one of the variables is, all the others are forced. But now we're going to have both x and y can be chosen independently of each other. So I'm going to talk about domain then. It says find and sketch domain of f of x, y equals square root of x plus y plus 1 over y minus 1. And also find f of 3, comma 2. So how do we do this? Well, if I look at this function, we should remember rules for domain. Alright, so it's f of x, y is square root of x plus y plus 1 all over y minus 1. Right? Am I remembering that right? Yeah. So the rules for domain, if it's not stated, then you pick domain to be the largest possible. So you say, well, let's figure out what causes problems for this. Well, there are three rules. Denominator cannot be 0. A thing under a square root has to be greater than or equal to 0. Whatever's under here is greater than or equal to 0. Same is true for logs. If you have a log, well, then it has to be, the thing inside has to be strictly greater than 0. So those are your main three rules that we have in this class. There are also some trig functions have domain issues. But do we have any of them here? Well, okay, we have a denominator. So y minus 1 is not allowed to be 0, which means y is not allowed to be 1. And then for the square root, x plus y plus 1 must be greater than or equal to 0. I'm going to solve that for y and say y is greater than or equal to negative x minus 1. Well, what does this look like? Y is greater than or equal to negative x minus 1? Well, first off, let's be clear here, this is f of xy, so domain is in R squared. So if we want to sketch what the domain looks like, we're essentially saying I want to draw where all the points that you're allowed to plug into this. Where would they be? Well, we've got these two rules here. So it says y is greater than or equal to negative x minus 1. Now, the way to draw an inequality is you first write as an equality. If I say y equals negative x minus 1, that's a line like this. That doesn't, I messed that up. That's the line y equals negative x minus 1. Now, we need to shade one side or the other. Since it says greater, y is greater, so we go up. But we also have this rule, y is not equal to negative 1. So the equation y equals, I said negative 1, I'm going to say 1. That's not in the domain. So we need to, I'll put a little dotted line here to indicate that this line is not part of the domain. So the domain looks like this. Everything up here, except for that line. Any point that's above this blue line and is not on this red dotted line will work. How do we know that? Well, the easiest thing to do is just pick a point that's in there and test it. So let's say here's a point, 0, 2. Does it work? Let's see if f of 0, 2 works out. Well, it becomes square root of 0 plus 2 plus 1 over 2 minus 1 is square root of 3. That's a real number, so it's in the domain. If we picked on the other side, we would have gotten a negative on top, and that's not a real number. Okay, the other part says, what is f of 3, 2? Well, we just plug in 3 for x and 2 for y, so we get 3 plus 2 plus 1 over 2 minus 1 is square root of 6. Okay. So, this was a sketch of the domain. We did not sketch the graph of the function. The graph would be in 3 dimensions, because it would include the range as well. So, find the sketch domain of this function. X ln of y squared minus x. And also find f of 3, 2. Alright, so once again, we've got 2 pieces, and we want to work out the 2-dimensional domain. Always ask yourself, how many dimensions in the domain? Input is x and y, so unless it's some really weird case, the domain should be drawn in 2 dimensions. Even if it is a weird case, you'd still draw it in 2 dimensions, because it couldn't be more than that. So, x ln of y minus, one of those was squared. Which one was squared? Y squared minus x. Okay, so let's, x, y. 2 dimensions. Domain, you can make a little note this. Domain is in R2, meaning you're going to draw a 2-dimensional graph to put the domain on. You do that just by counting how many variables there are in the input. Okay, so this piece, the x, doesn't affect the domain at all. You can plug anything into an x. This piece, the natural log, that's another story. We know y squared minus x has to be positive. That's the same as saying y squared has to be greater than x. Well, so you ask yourself, okay, what kind of shape is y squared equals x? Well, that's a parabola. It opens right, because x is always positive. And vertex is 0, 0. So let's put the vertex there. Now, since it does not say equal here, it just says greater, so we do a dotted curve instead of a solid one. And then we ask, which side do we go on? Now this can be written as x is less than y squared. See, this one when it says y squared is greater, I don't think thinking up and down is good here, because, you know, parts of this are above the parabola, but parts of it are below. But this way it says x is less than y squared. X is less means left. So we'll shade to the left. Now, if that doesn't make sense to you, you just do a test point. You just say, okay, let's say I don't have any idea which side to shade. Well, I just pick a point that's on either side. Let's pick this point, 1, 0. does this work? F of 1, 0 would be 1 times ln of y squared is 0 minus 1. That does not exist. So this point is not in the domain. Therefore, it must be the other side that's in the domain. I think of it as like when you're doing Microsoft Paint, the little fill tool. You find one point that's in the domain, you click it, and it fills everything all the way to the lines. So, if you tried negative 1, 0, that would be in the domain because it would just flip this minus to a plus. And I'll give you 0. Okay. So, let's keep going. On the f of 3, 2, I plug in 2 for x, 3 for y. Let's do it real quick. Would be 2 natural log of, no, 3, 2. Would be 3 for x. Natural log of 4 minus 3 would be 0. All right. Domain and range. Find domain and the range of this. F of xy is square root of 16 minus 4x squared minus y squared. 16 minus 4x squared minus y squared. F of xy. Now, first you do, count the input variables. 1, 2. So domain is in R2. That's shorthand, that's subset containment. It just says the domain is part of R2. There was a square root on here that I'm leaving off. Let's fix that. There we go. Okay, so we say it's a square root, so that means we need the thing inside the square root to be non-negative. It's allowed to equal 0. Square root of 0 is just 0. But it can't be negative, so we'll do that. All right, so let's solve this out. This becomes 16 greater than or equal to 4x squared plus y squared. I'm going to divide out the 16 because this is looking like one of our conic sections. We get 1 is greater than or equal to x squared over 4 plus y squared over 16. So x goes out to square root of 4, which is 2. And out to negative 2. Y goes up to square root of 16, which is 4. So 0, 4, 0, negative 4. It's an ellipse. Since it's equal here, I'm using a solid curve, not a dotted one. Now, do I shade inside or outside? Well, let's pick a point. Let's pick the most obvious point, which is 0, 0. Is 0, 0 in the domain? F of 0, 0 is square root of 16 minus 0 is 4. Yes, it's in the domain. Could also have plugged in here and say 1 is greater than or equal to 0. That would work too. So the domain is everything inside this little football here. Okay. What else we got? What else do we have? Now the graph, I alluded to the idea of a graph earlier. What is a graph? Well, if you have a function from r squared to r, the graph is all the points x, y, z in R3, so f of x, y is z for any x, y, and d. So what does that mean? Well, it means that instead of just the domain, we also want to include the range. So when we were looking at two-dimensional cases, something like, y equals x squared, you would have a bunch of points here in 2 dimensions. This is the graph, this curve here that we draw, because it includes all the x, y pairs. But if instead we have z is a function of both x and y, we can't just have x, y pairs. We need x, y, z triples. So that means if we're going to do the graph, we'd have to do in 3 dimensions somehow. And we've done a few of these already, like the ellipsoid or the paraboloid. We've done this is a paraboloid. We've also done ellipsoids. Point is, we're including both the domain and range. Now, if we had a function like w equals f of x, y, z, that's 4 dimensions. It's a little harder to graph a 4-dimensional figure. There are ways to do it using colors and such, but the more dimensions you have, the harder it gets. Alright, so let's do an example here. Sketch the graph of f of x, y equals 6 minus 3x minus 2y. Okay, 6 minus 3x minus 2y. So, what we are saying is that we want to put whatever, if you plug in an xy pair, we need to combine it with the z that comes out from this. So we need z equals 6 minus 3x minus 2y. We can move these over and get 3x plus 2y plus z minus 6 equals 0. And so instead of having a plug in and take out thing, an input-output, we just have this equation, which hopefully recognizes the equation of a plane. And so if you want to graph a plane, the way I would recommend doing this, since we now know how to find the equation of a plane, the way I would do it is mark all intercepts. That is, all the places where it crosses one of the axes. So on the x-axis would mean y and z need to both be 0. So let's plug y equals z equals 0. We get 3x minus 6 is 0. So x is 2. So here's a point. 2, 0, 0. Now let's do x and z are both 0. Then we get 2y minus 6 is 0. So y is 3. So I'll go a little farther out. 0, 3, 0. And the last case is the z-intercept. So let's say x and y are both 0. Then we get z minus 6 is 0, so z equals 6. So that's up here somewhere, 0, 0, 6. So let's just connect the dots. Connect these dots here, and, well, we get a plane. We got a triangle, and I would shade it in to indicate that it keeps going. Maybe put some little dotted lines off to the side to indicate that. But that's the main, that's how I would draw a plane. I would just draw the piece of it in the first octant, draw the intercept, we can show the part where everything's positive, and then just understand it keeps going. Alright. So this is not too different than the graphing we've done before. We've talked about level curves already. A level curve is a solution set of the equation f of xy equals k. And if we collect them, we get a contour map. So this little picture is supposed to show how the contour map gives you an idea of the shape. Over here, I can see the contour lines are bunched really tight, so it's really steep. Out here, they're spread out more, so it's probably a lot shallower, a lot more What's the opposite of steep? Steady, relaxed slope. Okay. Yeah. So, and that works as long as they are the K's are evenly spaced. So it's like, when we're picking K's, we all go like 1, 2, 3, 4, 5. You wouldn't want to skip K's because then that would mess up the shape of the map. It would distort it. Okay. So we've done this before. Draw some level curves of this shape. 16 minus 4x squared minus y squared in a square root. So, yeah, if we set that equal to a k, then we square both sides. 16 minus 4x squared minus y squared equals k squared. And so we can get it as 4x squared plus y squared equals 16 minus k squared. And then we talked a little about this before. Just pick some k's here. If k equals 0, then we get 4x squared plus y squared is 16. Divide both sides by 16, and we get x squared over 4 plus y squared over 16 is 1. We already saw this one. Y goes to 4, x goes to 2. The k equals 0 happens to also be the boundary of the domain, and that's because the square root can only take things that are greater than or equal to 0. So there's k is 0. And then you say, what's the largest k could be? Well, the largest k would be 4, because if you did that, you'd get 16 minus 16 is 0. So k equals 4 is just a dot. Then I'm okay with you just sort of guessing on the other ones. There's a k equals 1. K is 2. K is 3. I think that's fine. You could get a lot more precise if you wanted to by just working out exactly what the solutions were if you plug in a K of 1 or 2 or 3. But I don't think you need to. I'm fine with this. All right. Here, let's sketch a contour map for z equals y squared minus x squared with at least 3 lines. Z equals y squared minus x squared. And if you think this all seems familiar, it does. There's some repetition in math in general. Okay, so we want to pick different values for z. So let's say z equals 0. Then that gives us y squared equals x squared. So y equals plus or minus x. So these are the zeros. Now let's pick a 1. Z equals 1, or k equals 1. 1 equals y squared minus x squared. So y squared is 1 plus x squared. Y is plus or minus square root of x squared plus 1. Now what shape is that? Well, this turns into what's called a hyperbola. And this was something you could review from pre-cal or come to calc table or pre-calc table and talk about it. But we have, as x gets larger, y gets larger as well. So it'll look kind of like 2 hyperbolas. And you can see as you add the 1 here, it'll shift the positive 1 up, shift the negative 1 down. So if we change k to something other than 1, so like k equals 2 would be above there. What if k were negative? What if we said k is negative 1? Well, then you have -1 equals y squared minus x squared. I would multiply this out by -1 to get 1 equals x squared minus y squared. And it's kind of the exact opposite of what we had here. We had y squared equals square root of x squared minus 1. Or that's y, sorry. With a plus or minus on that. So what happens here? Well, this time, hold on a second. X gets larger. Yeah, this time x has to be positive, so it ends up going this way instead. Could have also done it like this. We could have solved it as x equals square root plus minus of y squared plus 1. And that would just be a reflection of what we had to begin with in blue. So, yeah. This, if you don't remember, what is it? X squared, or let me, x squared over a squared minus y squared over b squared equals 1. These are called hyperbolas. It looks a lot like an ellipse, except it's a minus instead of a plus, and that completely changes the shape. All right, let's do a couple more examples real quick, and then we'll be done. This is just an application, Cobb-Douglas function. So this is when we've got a trade-off of two variables. So you're running a business, you have to spend money on labor, you have to spend money on capital. And if you spend more on one, you can spend less on the other. You buy more machines, you don't need to hire as many people, and vice versa. And so you get level curves here by setting up this equation here. B equals L to the alpha, K to the 1 minus alpha. Where alpha depends on what kind of industry you're in, so does B. L and K are the two variables. Sometimes call them indifference curves, because as far as your spending is concerned, it doesn't matter which arrangement you use. So I would say stop for a minute, go to our graphing software, and plug this in. B, L to the alpha, you whatever you want for B. Just put 1, I guess, would be the easiest. Put L to the 0.25, K to the 0.75. Or if they don't have L and K, just use X and Y instead. L and K for labor and capital, but you can use X and Y, it's just as good. And it will show you a curve in 2 dimensions. And that curve means all the places where alpha is 0.25. So all the places that would give the same amount of productivity. All right, I want to show one more example. Find the domain of this function. X over 9 minus x squared minus y squared minus z squared, square rooted. What is this function? Well, we do not have any logarithm. We do have a square root and we have a denominator. Square root says the thing inside has to be non-negative. Denominator says it also can't be 0. So domain will just be whatever makes that denominator positive. So we say 9 minus x squared minus y squared minus z squared has got to be positive. Well, that's the same as saying 9 is greater than x squared plus y squared plus z squared, or vice versa. X squared plus y squared plus z squared is less than 9. Well, this is, if you did it equal, x squared plus y squared plus z squared equals 9, that's a sphere. So we will draw a sphere in 3D. With radius equals 3. So 0, 0, 3, 0, 3, 0, and 3, 0, 0. Now, since it doesn't say equal, it's a dotted sphere. And since it says less than, we're going to shade the interior. If it said greater than, we would shade the exterior. We know this because if we plug in 0, 0, 0, plug in 0, 0, 0, that's in the domain. It becomes 0 over 3, which is 0. All right. Thank you. I will see you in class.